to the cloud and share screen. What's an internet? I don't know. We'll find out. That does bring me up to a good point. I am going to have trouble playing this keynote and focusing on chat at the same time. I actually don't even get to see you guys. Kind of annoying. If you've ever used Keynote before, it takes over your whole machine. So if you do have any questions, go ahead and unmute yourself to ask. I don't mind interruptions at all. And I'll also try and periodically leave some time for questions. Cool. So let's get started. Networking 1, the internet, and how we're going to think about it and how to think about how it works is what we're going to be talking about today. So an outline, the internet, right? How we use the internet, clients and servers as this whole kind of model for systems and communications, how we render a web page, how your browser specifically renders a web page so it actually like looks like the internet, looks like things. We're going to talk about DNS, or how your computer is actually able to find servers, right? How it's able to find their addresses. We're going to talk about models and why we use models. Specifically, 2 different models. We're going to talk about some protocols. Bring these back from way back when you guys studied NET. So that's TCP and UDP protocols. We're going to talk about the TCP over IP model. And lastly, we're going to finish it up, wrap everything up with the implications for security and what that means for us. So that's our lecture for today. Let's see. How do we actually use the internet? So here's you on your machine, and you want to use the internet. So you fire up your browser, and you get something that looks like this, and you type into that URL bar www.google.com, and maybe you put an http:// first. Because you want to be old school a little bit like that. And what you're really saying to your computer is, I'd like this, please. I'd like whatever this resource is, please. And I'd like you to render that on my browser. And so somehow, somewhere, at some place in the world, there is another machine that you're talking to, and it's going to make a response and say, here you go. And all of this communication is facilitated by your internet service provider. And pretty much everything on the internet is going to work this way. You ask for something, and some other machine somewhere in the world responds to you. And your ISP is what's facilitating this kind of communication. All right, high level there. Then finally, you get this on your screen. You get the actual page for Google on your screen. So let's talk a bit about clients and servers. We're going to put some terminology, some actual words on this, some vocabulary. And, I'll be honest with you, this vocabulary, there's nothing mind-blowing here, right? Everyone's been to a restaurant and understands the relationship between the client and the server. But what we're doing now is just applying this to the internet and to machines. So big surprise, clients make requests. They ask for things. And our browser, in this case, is what's going to be the client. It is making the request. Specifically through the URL bar, we're specifying the request to make. But there are other ways we can make requests. There's a command line tool to make requests that you guys are going to get a little bit familiar with. So you can actually ask for the internet through your command line, and we'll do that later. So you could use curl. Now servers generate responses, right? No big surprise there, right? You ask the client asks for something, the server serves it up. And what they do here is they interpret the request, and based on that request, they try and generate an appropriate response to you. Now I say try and generate an appropriate response, and there's people who, software engineers are paid to write code for servers to generate appropriate responses. But sometimes servers don't necessarily generate appropriate responses, right? Sometimes you can send a request and things might not come out right. You can imagine this in a restaurant. If you go to a restaurant and, maybe you want some soup, you order ramen, right? You have some ramen soup, some chicken ramen, and the server brings you chicken noodle soup. And it's like, well, that's not quite exactly what I wanted, but it's still the same relationship here. I asked for something, server delivered it, and maybe it wasn't the necessary appropriate response, but there was some response. So same idea is happening here with the internet. And specifically, all of the responses that we're generally getting when we're asking for things over the internet are going to be what we need, what your browser needs to render the web page, to actually put everything on the screen, because there's more than just text there. So here's what happens. same idea, right? You on your computer, you are the client, some other machine somewhere else are the server. I make a request, I get a response from the server, and that's it. But that's not the whole story, right? A request and a response, I'm like glossing over some things there. How does this response somehow turn into a web page that gives me all of my functionality? How does this response give me, you know, a whole banking app, right? So let's talk about that. There's three major components of a web page that we take a look at. There is the HTML, which is the actual content and its associated metadata. There's the CSS, which you can think of as the styling data. And then there's the JavaScript, which is all the logic. Now, it might be useful if we take like a way trip down memory lane when we talk about the internet first being created. When HTML was first the thing, I want to say like 1989 or something like this is when it's first coming out, the first web pages, and they were just HTML like 0 point something. And all it was essentially text and specific metadata about that text. You could say this text is a title, this text is bold, this text is a list of texts, an ordered list of text maybe. And that was all the internet was. There were links, right? You can go from one page to another. You can imagine Wikipedia without the images, because if you'll notice when I was telling you everything about HTML, I didn't say anything about images. In the original HTML, there were no images. This was something that got added into it. So it used to be, right, you'd make a page, you would put some content on it, and you would put some metadata associated with that content, and that's all the HTML. And this is actually, if we follow this link here, which I'll grab, this will bring us to this page, which is, I believe, one of the original HTML pages on the internet. And you've probably seen pages like this before. This is when they don't load with any of their CSS. And you just get all the raw content. So I'm going to actually do a right click here and go to view page source. So this is what my browser actually renders to me to view. But this is what it's interpreting. You'll notice that there's the actual content here, right? It says the World Wide Web Project, and this is wrapped up in a title tag, right? And where do I find that here? Well, that's right, this up here. It says the World Wide Web Project. It's the title of this tab. You could say World Wide Web here. Where's that? It's wrapped up in a H1, which stands for header. What is that? That's this part right here, this H1. Right? So that's all the content and all of the metadata associated with the content. Cool. What about CSS? Let's go look at what that might look like. I'm going to go to example.com. Right. You can see this page is a little bit more interesting, right? It has actually like some nice rounding over here. There's some color in the background, right? This looks like maybe a slightly different font. I'm not sure. But what we can do is, again, I'm going to right click and I'm going to view page source. I'm doing this in Chrome browser, by the way, but you can do this in Firefox or pretty much most browsers. And what I want to point your attention to here is this part, this that looks a little bit different than everything else, right? You got some weird squiggly, some curly braces going on here. You've got some stuff that doesn't look like the rest of it. And this is CSS, or cascading style sheets. And quite frankly, for us as security folks, it's not super interesting to us in general. It's how we make the internet look good. It's how we style pages. It used to be, when everything was just HTML, if you wanted to change the color of all of your paragraphs, you would have to find all of your paragraphs and, you know, set some color attribute on them. Now, if you wanted to set all of your, you know, body to a particular color, right, you could just put in this style sheet and it'll say, oh, everything that is a body tag will have these properties. Again, I don't want you to worry too much about it. There's people whose whole job is to make stuff look good on the internet, and they do a lot of CSS work. But it's important to know this is what CSS is, this is what it looks like, and that's what it does. It makes things look nice. Cool. And that's what makes this like nice gray color sort of stuff, makes these rounded borders here. Okay, and then the final part is the actual JavaScript of the internet. Let's take a look at what that looks like. I'm just going to go to a more interesting page like NewYorkTimes.com. Right, there's a whole bunch of stuff happening here. You see, you know, things are changing here. Images are loading. Right, I'm just going to view page source. There's going to be a whole lot of stuff that comes up because this is a big web app. And really, what I want to kind of bring your attention to right here is you see this script tag. Let's make this a little larger. Larger, please. Larger, please. maybe too large, go back. Let's find it right here. Oh, there we go. No, where'd it go? I want that script tag. Okay, here. You see there's a tag that says script, and you see some code here. This is code that's going to be doing stuff around your browser. Maybe it'll be moving some of the elements on the page. Maybe it'll be opening up menus. Maybe it'll be sending other requests. But here's where here's where logic on web pages live. Sometimes they're inside script tags. Sometimes they're on whole other pages. Like, let's see if I look for script. Find a whole bunch of them. Source equals, right? This is saying, hey, there's some script over here, grab it from this source, this page. So it doesn't have to be right here. It's just saying, this is what JavaScript will look like. And this is the third part of modern web app. Cool. Let's get back to the keynote. Do you have any questions on those three sort of pieces needed to render a web page? Cool. We'll look at them, and you guys will be looking at some more of them later today. So big takeaway from this is clients make requests, servers make responses. It's not mind-blowing, but we're applying it to the internet and machines now. And the three parts that are necessary to make your modern web app is the HTML, which is all of the content, the CSS, which are all of the styles, and the JavaScript, which gives you all of the logic necessary. Okay, I lied a bit when I told you how the internet works, right? There's some usability issues here, right? So here's you, again, on your computer. And you go in to type into your URL bar and you want to go to google.com. But really, if you remember way back when, there was this thing called like the OSI model, and we talked about like internet protocol. And we needed to know some information to be able to contact another machine. What did we need to know? Anyone can just go ahead and unmute yourself and tell me. What information do we need to know to talk to another machine?
Would we need like the IP addresses?
Boom, that's what we need, right? Google.com, my computer doesn't know what Google.com is. This is like if you go into a taxi and I say, take me to Frank's house, right? Taxi driver doesn't know what Frank's house is. That is what I use to make it easy for me, right? Everyone knows, oh, Frank's house, maybe it's this address. So we need some kind of system to translate a string, right, of www.google.com into an actual IP address so the computer knows how to address it, right? So imagine this whole kind of like packaging center, right? How is everything going to know where it needs to go? And so we've got this great system and a relatively complicated looking image, but let's talk our way through it, and I think it'll be a bit more simple. I'm actually going to ask you guys this question at the end of the course. I'm going to ask you something like, oh, so can you tell me how does DNS work? And hopefully you'll all be able to give me a nice answer like this. So what is DNS? Let's follow this chart. We're going to start at the top left where it says example.com, and we've got that little machine there that someone's working on. So they're making a request, and they would like the resource from example.com. And like I just told you, computers, they don't know example.com. They know IP addresses. So the computer is going to ask its local cache, its local memory, and be like, hey, do I know the IP address of example.com? And in this situation, we're going to say it doesn't know it. So what it's going to do is it's going to make a request to a DNS resolver. It's going to say, hey, DNS resolver, what's the IP address of example.com? Please tell. And this DNS resolver is going to check its cache. In this example, we'll say doesn't know what it is. So it's going to have to find it out. So the DNS resolver is going to ask a root server for some information. So if we know about IP addresses or domain names, that they get resolved from backwards to forwards. So first we're going to ask the root server. This is like the starting point for every domain name to figure everything out. There's 13 root servers. They're like around the world. You can kind of Google it. It's actually pretty interesting infrastructure. But first you ask the root structure for the information that I need. Roots, and that is, if you look at number 2, that's the second request. So DNS resolver makes a request to root server responds. but we don't have the full answer yet. We need the TLD, the top level domain. This will be like the .com, the .gov, right? That area. So we're going to send another request. That's request number 4. Sends to TLD server. TLD server responds with number 5 to the DNS resolver. We're almost there. We don't have everything yet. You know, we got to get the last part, the example part of the example.com. So we send one more request to what's called an authoritative name server. It's not actually, it doesn't say that on this chart, but that's what it's called. It's really these servers that you go to when you buy a domain name, right? This is what gets updated. And so we send that request to the authoritative name server. That's number 6. And then we finally have the complete answer, right? Once we have that complete answer, that DNS resolver has the complete answer, it sends the response to you. That's number 8. And now finally, you know what example.com is. You know what the IP address of example.com is. So you can make a request to that's number 9, to the server that you wanted. And number 10 is the response from that server. Now you'll notice there's 2 different colored arrows, numbers 1 and numbers 8 in between the example.com and the DNS resolver. It says that they are recursive query. Can anyone in their own words just tell me what recursive means?
Pretty much something that happens over and over again.
Yeah, I think that's a pretty good description, right? It's something that's going to keep happening until it's done, essentially. So the recursive query is that's what the DNS resolver is doing. It's going to keep asking until I have the full IP address, right? That's why it's called recursive. And then you'll see the root server, the TLD, and the authoritative servers are all iterative queries. So we're going to keep building until we finally get the IP address, and then we'll send it to the user, and then they can finally use that IP address to contact the server. Once we do all of this, we're going to save that IP address in cache so that we don't have to do everything over again. You know, maybe we'll save it for a few hours or a few days so that next time you want to go to example.com, your computer already knows what the IP address is. Okay. Do we have any questions on this specific image? I know it's like there's like a lot of arrows and numbers, but I think if we just think of it as, hey, you're going to ask the DNS resolver, it may or may not know. If it doesn't know, it's got some boys that he's going to ask to get the answer. Once it gets the answer, it lets you know.
Would the server be just like the database?
The server at the top right would be whatever example.com server, right? But good question. It could be, it could be whoever we're asking. Cool. Let's talk about the tools we'll be using to interact with this DNS system. There's 3 of them. My suggestion to you is pick one of them and make that one your favorite. They all do really the same thing. Yeah, they all really do the same thing. I would say Host is slightly easier to use, and by slightly, maybe you put in one less argument than the other ones or something like that, right? Dig, I will say, gives you the most information. So sometimes that's useful. But that's really all I have to say about these 3 tools. You will be using them today, and you can solve all of the problems that need them with just one of those tools. But there's 3 of them, and I want you to at least be familiar with all 3 of them. Okay. So before I go on to why we use models, do we have any questions on DNS or the internet or clients and servers? And if we don't have questions, that's okay. I know we're probably just thinking about them, or if we have any thoughts about them, go ahead and let them out now before we keep going on.
Why wouldn't the server do everything, like go to the DNS, do everything on the DNS side, and then bring it back to the client, as opposed to the client asking the DNS lookup?
Okay, because the client does not know the server's address. It's the situation where I get into a taxi and say, take me to Frank's house. Taxi driver doesn't know how to get to Frank's house. And we have such a system, client and server, where as Frank is the server, he can't just come to me, right? I have to go to him and get stuff. So does that answer your question?
Yeah, thanks.
Cool. All right. So I have a question for you guys. One, have you guys seen this movie? Zoolander?
Yeah.
Okay, someone's seen it at
Yes.
least. All right. If you haven't, you should probably take a look at. I think it's hilarious. It's like silly, stupid, funny. But what I want us to think about is, why do we use models? Can anyone give me why do we use models at all?
We use models to represent complex systems.
Great. Yeah, that is exactly correct, right? We use models to represent complex systems. It gives us a bit of abstraction, so we don't have to think about all of the nuances and complexities in the system. We could focus on specific kinds of problems and not worry about everything else. Like, I don't know about you guys, but I cannot think about every single thing happening at the same time. Right? I have to focus only on what's right important and what's right next to me, and it makes it very easy. So with that, I'm going to show you the two main models that we're going to be using. And that is the OSI reference model, which you guys are already familiar with, right? It's the model that has all those layers that you tried to memorize and tried to associate with something, probably a protocol. And then we have the TCP IP conceptual layers. Here's I don't know if it's really a hint or just here's the observation, right? They're kind of the same. If you're looking at it very closely, it's just one of them is a little bit fuzzier than the other. I'm going to reference both models, but most of the time in my brain, I'm thinking of the TCP IP conceptual layers. And so what the difference is here is on the right side, on the TCP conceptual layers, yes, there's a data link and a physical, right? There's cables, of course, but I'll just worry there's a MAC address, right? I won't worry about how the data is actually getting around, right? I'll abstract that away and just say it's just a network interface. You'll see network and transport, they stay the same. But then up on the application level, you guys, we probably remember HTTP and HTTPS, and we say that those are both at the application level. Well, HTTP is one protocol, and HTTPS is the same protocol that sits above it on another protocol called SSL. That's complicated, and it really, that complication doesn't make my life easier. It doesn't like make me think of things I needed to, right? So I'm going to kind of abstract that away and just say application layer. And we're just going to think of things as these kind of like 4 layers of network interface, which is where like the MAC address live, and kind of like the physical address. We're going to talk about the network layer, which is where your IP address is. We're talking about transport layer, which are the ports. And then finally the application layer, which is kind of everything else. Okay, any kind of questions on this? I'm like kind of blurring the lines of like I guess I'm not really blurring the lines. I'm like, why do we use models? And it's to abstract things away. So I'm just kind of introducing this TCP conceptual model. Okay, let's talk about these two protocols, TCP and UDP, because these are both important. They both live here at this layer 4 of the OSI model on the transport layer. And this is how we actually send things from one machine to another, right? It's not enough for me to know where Frank's house is if I have to send a whole bunch of, like, if I have to send I'm trying to think of what a big package is that would be disassembled in parts, a table to Frank. I might have to send it in multiple parts, right? Multiple packages. And so we use TCP or UDP to send packages, right? Even though you may know the address, you may have to break it up and send them. And so what's important is that we understand the differences between both of these protocols. I'll say TCP is the more used protocol and the more common one, and the one we're a bit more familiar with, but UDP, there's uses for it. So the first thing we want to know about TCP versus UDP is that TCP is a reliable protocol and UDP is unreliable. What does that mean? It means if I send something by TCP, I can be confident that it will arrive. And if it doesn't arrive, I will be confident that I know it didn't arrive. Versus UDP, I'm sending stuff and hope you get it, man. That's it, right? It's just sending that data and hopefully you catch it. There's no part of the protocol that ensures that it actually gets there. TCP is also connection oriented, which means before we actually send any data, we're going to establish a connection. You guys have seen this as the 3-way handshake. you can imagine it as computers being like, first computer saying, hey, are you available to talk? And the second computer's like, yeah, I'm available to talk. And then you say, okay, let's talk. And then we start talking, right? That's TCP. That's what has to happen. UDP, like I said, not connection oriented. I'm just going to shoot data at you like a hose, and hopefully you're ready for it. TCP has what's called segment retransmission. You can imagine what that does, right? It's if something does not get sent, if segment doesn't get sent, we're going to retransmit it. We're sure, right? UDP, if a packet doesn't actually make it to its destination, too bad. I don't know about it. You know, I sent it. TCP has segment sequencing. This is adding a number to each one of the packets and saying which order it'll come out at. UDP, we're just not going to do that. We're just going to send everything over, you know, in any order. And so the benefits or drawbacks of TCP is there's lots of overhead, right? We need to do this three-way handshake. We have to add a little bit more data to everything to make sure it gets in the right order, right? Because we have to put in order on things that we're sending. And UDP, there's very little overhead. So why would I use UDP? Anyone have any ideas on why I might use UDP versus TCP? Because I'm reading this and it sounds like TCP is everything I want.
If you want to stream something, I guess UDP would be a better option.
Boom, right? Right, we're using UDP right now. We're just streaming. I'm pretty sure we are at least. And if packets get lost, they don't get resent to you, right? If like I get slightly laggy internet, you just lose those packets. They're gone. So very little overhead, right? It's imagine UDP as like, you know, you take your water bottle, you open it up and you just pour it in and whatever gets in the mouth gets in the mouth. And, you know, there's a use for that sometimes, right? If it's really hot, maybe that's what you want. But you know, that's the reason it's not as common as TCP. TCP is the more common one, and there's a bit more overhead to it. And it's so common, that's why we also have this TCP over IP model. Okay, so here we've got this great joke. Here, I'm not going to read it out loud because I hate people that read out loud jokes. I don't hate people that read out loud jokes. I'm sorry, I don't hate anybody. But I dislike people that read jokes out loud. So I'll just be quiet for a minute and let you read. All right, I see people shaking their heads, laughing or not laughing, cringing maybe. All right, but that's the idea here. UDP, there's no order. We're just sending data out. Hope you get it. TCP, we're going to make sure that all the data gets there. We're going to make sure it gets there in order. We're going to make sure, you know, there's a connection, and that's important to us. Okay, so let's talk about like how this data kind of looks and how to kind of imagine it in this image right here. Right, both TCP and UDP get sent over IP, right? If I go back, you can imagine this, right? The TCP and UDP are on that transport layer. They're like sitting on top of it. So the way you kind of want to imagine this data is like, kind of like wrapping the data in a package over and over, right? So if we look here, and I wish I could kind of point at the screen, but if you look at that Ethernet frame, you see there's EH, IH, TH, and data. All right, the data is the actual thing that's going to get sent, that the end person might be interested in, that the application is probably interested in. Wrapping that data, you're going to put a TCP header, right? It's like wrapping it up in a box. Wrapping up that TCP header, we're going to wrap it up in an IP header. It's like wrapping that up in another box. And then you wrap that up in another header, which will have the Ethernet header and have the MAC address information. And this way, by wrapping everything up, if we look back here, each layer, or really the layers on the right-hand side, don't have to worry about what the other layers are doing, right? Transport layer only has to worry about network and application. Doesn't need to worry about MAC address, right? It's already wrapped up in there. So think of it as like wrapping up this data by adding either another header, sometimes we add another trailer at the end, but just really wrapping it up in another box. So this way, something that has to worry only about MAC addresses, like switches, you know, they're like, oh, right, this says go to this MAC address, and I'll just forward it there, right? Routers that might only worry about IP addresses, just worry about IP addresses. And ports and TCP worry about what they worry about. Cool. Let's see. We can take advantage of a lot of these protocols by using a tool called NC or Netcat. It's It's great. It's fantastic. It is our Swiss Army knife of TCP/IP connections. NC is fantastic. And I want you to imagine it as your little servant that you can go off and send to do important TCP/IP things. Like you could tell Netcat to be like, hey, Netcat, can you go knock on this IP address at this port number and tell me what it says? It's going to go knock on the door and it'll say what it says. It'll set up a connection. You can also say, hey, Netcat, can you listen on my machine on a particular port number? And if someone reaches out to it, you'll let me know. And Netcat can do that too. So Netcat can act as both a client, sort of, right? It will reach out. And Netcat can also act kind of as a server where it'll just like listen. Open up a port on our machine. And we're going to use NC. It's going to be a fantastic tool. You'll use it a few times, more than a few times throughout the program. Cool. So let's talk about the security implications for all of this stuff. Another question I'm going to ask you at the end of this is what is cybersecurity and how it ties into all of this IT stuff. And really, it comes down to these three concepts of confidentiality, integrity, and availability. And everything you do is to support your business, your organization through that, through keeping things confidential that need to be confidential, right? Through keeping the integrity of systems, so someone can't change things unless they have permission to, and making sure that people can get the resource that they need, making sure that things are available. And we can kind of look at the OSI model as hackers or as defenders and see where we can attack different parts of CIA in the model. So for example, confidentiality, you can sniff packets, right? You could see data going over the wire if it's not encrypted. Integrity, you can spoof packets, right? Like I can make a request and say that my MAC address is something that it's not, or my IP address is something that it's not, right? Who's to say, like, why can't I do that? Of course I can. And then availability, making sure that the resources are available when they need to be, right? Like I can do denial of service attacks on things, right? Like I can cut wires, right, at layer 1 and then do denial of service that way. There's different layers of the OSI model that I can attack. And that's kind of what I want us to be thinking of as we're going through this. So in summary, we have a lot of protocols to facilitate communications. We have DNS so that we can resolve URLs or really dissolve domain names to IP addresses. We have like the HTTP protocol for doing things over the web. We have TCP and UDP for facilitating different forms of communication. But really, all of them pretty much use this client and server relationship where you're going to ask for something, server's going to wait for that, and then form some kind of response. We talk about IP as a protocol for transmitting data, right? It's at OSI layer 3, or it's in that TCP IP model as the kind of second layer after the MAC address layer. And we can encapsulate traffic. We can encapsulate traffic around that by adding headers and trailers. So it's kind of like taking packages and putting another box around it. Okay. TCP IP, we talked about being the most common packaging method. And why is it the most common? Because it's reliable, right? That's useful to most of what we're doing on the internet. But if we're doing other things, if we're streaming, if we're gaming, a lot of times those situations, we care more about like maybe input lag or things happening very quickly. And that's where we would use UDP. And we talked about the OSI model. It showed us kind of all of the different points in IT where our systems are vulnerable, right? We have the physical layers where things are vulnerable, just cutting cables. We have spoofing things at different MAC addresses. We want to be thinking of that OSI model and that TCP IP model throughout our entire careers as IT and cybersecurity folks. So let's look a little bit at what we're going to be doing today at our labs. Before I do that, though, do we have any questions on this lecture? Let me stop share real quick. Actually get to see you.
In our, sorry, quick question. In our pre-work, there was a text saying that there's a recursive resolver, which usually takes the form of your service provider or your ISP. Is that the same thing as a DNS resolver, just different words?
Yes, so the recursive resolver is your DNS resolver. It's usually set up by your ISP. There are public ones as well. If you look at, we'll always tell you to check your internet by pinging 8.8.8.8. That is a public DNS server that is run by, I think, by Google. And yeah. Cool. So let's take a look at what we're going to be working on today then. I'll share my screen. Okay. So here's me in my Kali. And we're going to be working on CyberLab today. Very exciting. Love CyberLab. And once I open up the workshop, it's going to look like this, right? So we had the pre-work here. You guys probably took some time last night to take a look at these things. And we're going to go to CyberLab and work on the problems here. And actually, Frank is going to be my partner, and we'll do the first problem together. So again, we'll always love demonstrating how to do the pair hacking, best practices sort of thing. So Frank, are you available?
Yep.
Cool. Cool. So I'm just going to get started. I'll be driving. Frank will be navigating for this problem. Usually it's good to agree on either how you guys like to work. Sometimes it might make sense to switch off every problem, but oftentimes you'll find some problems just take way longer than others. So it might be good to say, hey, you'll drive for 20 minutes and then we'll switch over sort of thing. Okay. So I'm going to grab this unlock code. And I'm going to go to CyberLab, and we're working on today Net1, which makes sense because that was the name of our thing, right? So we'll go here, and here are the problems first. The first thing you'll see is all of them are going to be locked, and you'll have to put in the unlock code here, right? I already unlocked it. So Frank and I are going to work on this first problem, Net1 CyberLab IP. And Frank will be navigating. So this question, Frank says, what is the IP address associated with cyberlab.fullstackacademy.com? And we need to give the answer in this form of FS and then I guess the IPv4 address because there's 4 dots. And I always like to look at the hint. You can agree with your partner whether or not you like to look at the hints first, but I think that they're usually pretty useful. And this hint is telling us to take a look at either the dig command, the host command, or the lookup command. All right, Frank, so what should we do?
Well, let's take a look at these commands, right? So let's open a terminal and let's just, let's look at the man pages for these and see which one we're going to mess with.
Okay. Is there one you'd like to use?
Me personally, I like host.
All right, let's try host. Okay. DNS lookup. All right, that's what they said. Simple utility. I like the synopsis usually because it kind of tells you what you should be doing with it. Maybe there's examples. What should we be looking for?
So just looking at, if you scroll back to the top and if just looking at those, how the command is, so inside those brackets, those are the options, right? And it looks like we can just say host. I don't think we need any ports or anything. I think we could just give it host and then the server name, right? At the end.
Yeah, that looks right. Host and the server. All right, let's try it. Host. And I like to just copy and paste every time. Copy. Paste. Okay, says it has an address of this. That looks like an IPv4 address.
All right, can we just double check and let's ping it, the name, and see if that comes back as the address as well.
Ping.
Yeah.
Ping that address.
I mean the name rather.
Okay. cyberlab.fullstackacademy.com.
All right, so we got, well, it's resolving to that, although it's not answering the ping, but it's resolving to that. So I think that's okay.
All right, let's try it out. Let's paste that. Curly brace. Submit. Boom. Problem solved. Now, in this case, since we solved that problem pretty quickly, I would probably continue to drive. But, if we wanted to, we could switch off every single time. Any questions on like how we kind of solve that together? Cool. So y'all can take about 2 or 3 minutes to, use restroom or anything like that. I'm going to set up the breakout rooms and set up the pairs for you guys to work on the problems today. You're going to be working on the CyberLab problems pretty much through until lunch. And probably after lunch, we'll give you a little bit more time to work on these. And again, they're all in the Net 1 section. Cool.
Mm, mm, mm. Mm.
All right, so I've got the rooms set up. I'll open them now. Do we have any questions before I split you guys up and let you go at it? All right, in that case, have some fun. We'll be here. Put in a help ticket.